You
Hello,
can
people.
share your, yeah.
Okay. Uh,
Also, sorry, I forgot to say this. Throughout the class, if you need something, you can just private text me or give me
yeah,
a call.
yeah,
Either.
good. Hello, people. So, today we will be discussing grid type structures, or switch on your camera as far as possible. Like, it's better. Can you see the screen? Just oh wait, I haven't shared, have I? Oh, I have shared. Nice. Okay, so at any point, like if you have any doubts or you don't understand what I say or what I write, that's a very high chance. Just feel free to interrupt, no issues. So we'll be discussing grades. Also, it would be better if you could speak up instead of use chat because it's difficult. Okay, so we will be discussing grids. So basically, what are grids? So grids are basically structures which are arranged in a grid format. I mean, that's the basic definition. I'm aware. I'm sure everyone would know that. Like for example, you would call this a grid. Wait, what is this? Yeah, so I'm sure everyone knows what grids are. Like you can see them everywhere. Also, these are square type grid. There can also be points type grid. Wait, there is my laptop is having some scale issue. Can you see the screen?
Yeah.
Okay, sorry for the scale issue. So as I was saying, like grids can be like this square type thing, or they can also be like a set of points, or you can imagine lattice points in the Cartesian plane. So by lattice points, I mean those which have integer coordinates. So we'll be discussing colorings of grids, tiling of grids, and stuff like that. Also like some games on grids. So I'll just introduce some basic techniques that we use or something. So some coloring techniques are okay. So many times it's beneficial to like when the arguments seem very parity type, like it's either odd even sort. You can color this in a chessboard fashion, like color like this. These are black squares, and these are white squares. So that this coloring actually works for any m cross n grid. Oh, when I say m cross n, it means like m cross n or ulta, I mean, maybe, but it doesn't matter. I don't remember exactly, but fine, it doesn't matter. So this is chessboard coloring is one sort. So some things to note about the chessboard coloring is if m m cross n may if uh if it is odd cross odd grid, then all corners are of the all corners are same color, and also so you get more black squares than white squares. I mean that depends, if you color corner white you get vice versa, but basically there's an imbalance. Like you can see if it's 3 by 3 grid, you can see that there are 4 white squares and 5 black squares. So basically that is obvious because it's like 2n plus 1 cross 2n plus 1. Or if mn is even, like let's say we have a 2 cross 3 grid. That is the 2 cross, yeah. So now here we have an equal number, like 3 and 3. And if we have, let's say, what, uh, an even cross even, like these we will encounter many times. Like for example, assume something like a chessboard or something. This technique is called chessboard coloring. So these things also have an equal number of black and white squares. So the equal number makes life easy. So many times when you have parity arguments, it is easier to use this chessboard coloring. Also, like good thing is that all the neighbors, by neighbors I mean the neighbor of this square is 1, 2, 3, 4, like the perpendicular ones, one side to the left, up, down, right, left. They are all of the opposite color. So every time you make a move of some sort or something, you change a color. Okay, so this was about the chessboard coloring. Any doubts here?
No.
Yes, nice, great. So like now there is another type of coloring which is commonly used. I mean, not very commonly, but a good thing to know. Like, so if you have something of the sort 3m cross 3m, or let's for simplicity take 3m cross 3m. So you have something like, let's take a 6 by 6 right now. Okay, so like what you can do is this is sort of RBG. Okay, R means red, blue means blue, green means green. I mean, G means green. So, wait, what am I doing? So like you can see that this sort of coloring works because it is 3m cross 3m sort of thing. Yes, so this is the coloring. So like the good thing about this coloring is just if you have any tile of 3 by 3 cross 1, like by tile I mean something like this. Wait, what's happening? Why can't I write? Change color here. So like if by tile I mean something like this. So this is a 3 cross 1 tile. So if you place this anywhere in this grid, you can see that it will cover exactly one color of I mean one square of each color, right? Like for example, if you place it here, it covers RBG. If you place this here vertical, it still covers RB and G. So this is good in terms of like when you have a multiples of 3 type arguments. Okay, so these were the like common colorings. Now I just introduce some type of tiles. Okay, so what exactly is tiling? So, so tiling basically means that you want to cover the grid. So tiling basically means that you have a grid and you want to cover it using some tiles. So tiles are something that will cover the squares. So some common tiles or this is a 1 by 1 cross 1 tile. This is what we call a domino. Like sorry, does anyone want to say something? Okay. So this is a domino, even this is a domino, 2 cross 1, something. I mean, or maybe ulta, I'm not exactly sure, but it doesn't quite matter. Uh, so what a stromino is, a 3 cross 1 stromino is something like this. And another one which we will commonly use is, this is called a L tromino. This is a stromino. So this is what we have, like these are some common tiles. Also some others might be specified in the problem, like for example, you can get 5 cross 1. Or oh, also like even this might be quite common. This is a 2x2 tile. So like in many problems you are tasked to find a number of ways or something like that to tile the board using some of these tiles, or I mean they will provide you what you have to use or something like that. Like in many problems they say non-overlapping. In some problems they might be overlapping, but like it depends from problems to problems. So like this is some basic intro about tiles and colorings. Now like let us jump into some problems. Oh, are you guys familiar with induction arguments?
Yeah.
Yeah.
Yeah, nice. So like we can just begin with the questions. First question is, prove that for all n greater than or equal to 0, you can tile a 5 into 2 to the n cross 5 into 2 to the n board, or yeah, let's say board, using L trominos. Also, like when I don't specify, I usually mean non-overlapping, such that they leave exactly one square untiled. Okay, so this is the question. You might want to try this for some time. Let's give it some time. Okay, so for those who have already seen this question, I'll give a buffer question. Okay, so like this is sort of a game question. We will come back to this later. So you have say M cross N grid, and then this is a checker which you start from. Now players Arnaldo and Bernaldo take turns moving this checker one square orthogonally, like one at a time, and a checker which has been like a square which has been already been visited cannot be visited again. So Arnaldo starts. Let's just call them A and B. So A starts, and like he can move here, then B can move either here or here, and so on. And a player who cannot make a move loses. So you have to find out who can win. Also, like this is the first part of the question, and second part is you start from here, then who wins or loses. That's the question. Like if anyone has seen this, just tell me. I'll give another one.
Is the first player who can't make a move the person who wins or loses?
The first player who cannot make a move loses.
Wait, what's the meaning of like orthogonally means like perpendicular or like diagonal?
No,
Because
no,
like checkers go.
orthogonally means perpendicular. Like it's this or
I
this,
know that.
this.
Doesn't checker go like this?
Bro, checker is a checker. It goes anyhow. It likes like it goes how we want it to go. Or like, let's just say it's not a checker. Let's just call it, what, say it's a king. No, even king goes orthogonal. So, I
Like
mean, king goes diagonal.
chip,
Okay, you
chip.
understand.
Call it chip, man.
Okay, this is a new piece I have created.
Okay.
Okay, so I have people tried this question. Those who had those who had not seen it. Anyone has any ideas? Feel free to share any ideas if you have.
I have an idea.
Yes.
So we can start off with the a 2n by 2n board. I started off with that, and
2n, yeah, yeah, go on.
2 to the power n by 2 to the power n board.
Okay, yeah, go on.
So I checked with small examples, and we end up with always one square missing. So
Hmm.
like we can start with 4 by 4 like that. There's one square always missing, and then we can use induction to prove this.
Yes, like that makes sense, but how will you introduce this 5 here? I mean, this
I
5 is
was
an essential component, right?
Yeah, so I was thinking if we could break the board into 25 squares with by 2 to the power n by 2 to the power n individual
Okay,
board.
okay.
So if we could pair up any four of them or something like that to find out if there's exactly one square. So I thought I'd
Hmm.
start with the 2 to the power n by 2 to the power n board.
Okay, okay. So like this seems a good argument. So like let us say you start with, how do you erase? I can't erase. Hmm. Okay. So like let's say you start with 2 cross 2, right? So you can just tile it like this. So now you want to go to 4 cross 4, right? Okay, I mean let's just take 10 by 10. Like it is difficult to draw. So like when you are dividing into 25 squares, do you think it would be easier if you try it the reverse way? Like since you are aware that you need to use induction, like obviously, so do you think it would be easier if you could try it the reverse way, like divide the 5 into 2 to the n into 5? Like, what else can you do instead of dividing into 25 squares? Like for 25 squares, you will get a 5 cross 5 something, and then again you land in the same argument. Like let's say you divide it into something like 5 cross 5. So let's say that you divide it into this, where each of these small thing is a 5 cross 2 to the n thing, or 2 to the n cross 2 to the n thing, sorry. So now, now what can you say about this? I mean, okay, you can proceed with this argument also, fair enough.
I have a better argument. Can I tell that?
Yes, yes, sure. Go on.
The board is 5 into 2 power n, the board is there. So the total number of squares will be 5 square into 2 to the power 2n. 2 to the power 2n.
Yes,
So 25 is 1 mod 3, and 2 power 2n will always be 1 mod 3.
yes,
Therefore, the total number of squares will also be 1 mod 3.
yes.
Therefore, and since L dominoes are always 3, therefore 1 square will be left untiled at last.
Yes, like that argument is true, but how do you know that you do not end up with something like this? Like let's say you tiled something, and now only these 3 squares are left. So like now 3 squares are left. Okay, you can't live. Oh, let's say 4 squares are left. So now these four you cannot tile using an L domino, but now 4 squares are left, right? And also 4 is congruent to 1 mod 3, so that is just possible.
Yeah, yeah. Okay.
Okay, so I'll just give a starter. So what, like everyone, like I think everyone must have got the idea that we need to induct on n, right? Like just ask me if this is not clear why. Okay, so we need to induct on n, obviously, like someone said. So now, so what is the base case? You know, n equal to 0 is the base case. Can you try tiling for 5 cross 5 grid? Also, yeah,
I want to make another observation to continue the idea on dividing the board into 25 squares.
yes,
So, if we divide them into 25 squares, if we take a tromino of these squares, any three of these squares which is in the form of an L, these big
okay,
2 by n by 2
yes.
by n
So
board,
like this thing you are saying.
right? So so these three will not have a single empty space.
True, true. Like, could you just elaborate a bit? Argument is correct.
Right. So I proved that for any 2 by n by 2 by n, we always have one remaining square, which we can arrange.
Yes,
So that one singular square can be, so there's one in, okay, suppose we have three of these 2 by n by 2 by n squares in form of an L.
Hmm.
So we could have one of them in one corner, another one in another corner, and so all of those three, yeah, like that. So, and these three can form another domino on itself.
yes, yes, right.
So the problem boils down into finding if into proving that if a 25 if a 5 by 5 board can be split into dominoes where there's exactly one remaining square.
Yes, yes, true. Right. And that remaining square, yes, yes, true. That's true. Correct. Like, that construction is quite easy to find actually. Like, you can just try to do it manually.
Yeah, I've tried that. It works out. So I'm not quite sure if this is a complete proof
Okay,
because
okay.
I don't think it's a complete proof because we are showing it through an example.
Actually, okay, so this proof exactly does not work because your induction is sort of wrong, because here you are taking 5 cross 2n 2 raised to n into 5 cross 2 raised to n, right? And you divided this and then proved for this thing, right? And
Right.
in the next induction step, you will be using 2 raised to n cross 2 raised to n grid that you can tile this using the uh, L trominos, correct?
Yeah.
So like this does not exactly follow this from this side. Let's say plus one. Oh no, it's actually 2 raised to n only. So like this does not exactly, these are not exactly equivalent statements. So like what you can try to do is, yeah, go on.
Oh, no, nothing.
So like what you can, so this argument, this observation is very nice that if you can, so let's say I'll just write it down there. So if you have something of this sort, where you know that each of these can be individually tiled using tromino such that one corner square is left, then you can also tile this whole thing using trominos such that one corner square is left. Like you can just leave this corner square and take these corner squares here and tile them using a tromino, correct?
Right.
This is your argument. So like, so now from here, from n, you can go to 2n cross 2n,
Right.
right? So now if you just show for 5, put n equal to 5, and then you can go from 5 to 5 into 2 cross 5 into 2. And using this, then you can go to 5 into 2 square cross 5 into 2 square. So by induction, you are done.
I didn't get the last point where you said n is equal to 5. What are you defining n?
Okay, so n is like this side square. Okay, so let's say you would show for that 5 cross 5 square can be tiled. Okay.
Okay.
Now just consider a 10 by 10 square. Let's say this is 10 by 10. So these are all individually 5 cross 5s, right?
Yeah.
So
Okay.
and this is leaving corner square blank. So this is
Okay.
5 cross 5. this is 5 cross 5, this is 5 cross 5, this is 5 cross 5. Now using your argument, you tile this,
With
you leave
V1.
this corner, and now you induct on n, like, because now, so by 10 cross 10 you are done. So now again you can multiply by 2.
Okay, yeah, that's an idea. Yeah. I'll try working on that.
Yeah, I mean, so this boils down to exactly what you said, that if you show the for n cross 5 cross 5, you are basically done.
Okay. Yeah, that's
So
okay.
like it's just easy to show for this. I'll just show for the others. Something like this should work. No, I missed it. Is this 5 cross 5? Yeah, so you can see that this is possible. Like, exactly this square is blank. And so now you can, so you have shown for 5 cross 5. And now assume that you have shown for 5 into 2 raised to n cross 5 into 2 raised to n. You get this sort of grid. So each of these sides is individually 5 into 2 raised to n cross 5 into 2 raised to n. So you can leave them with a corner square blank. Make like you rotate them such that these are the corner squares, tile them using a domino, and discuss the remaining side. So now this whole thing has been true for 5 into 2 raised to n plus 1 cross 5 into 2 raised. Hence, true by induction. Did everyone get it?
Yes, sir.
Yes, like if there are any doubts, like you can just ask. Otherwise, we will move to next problem. Okay, nice. I assume there are no doubts. I believe you had a class on recurrence also, right? Let me just use some basic recurrence type of thing. Not exactly. So the question is now that there is a 2n plus 1 board, or basically, I mean, I just define the problem first. So you have 3 types of tiles available. You have a 2 cross 1 blue tile. You have a 1 cross 1 red tile. And you have a 1 cross 1 green tile. And like, so define Tn is equal to number of ways to tile a 1 cross n strip grid, whatever. So now you have to prove that Tn divides T of 2n plus 1 for all n greater than equal to 1. Does everyone get the problem, or should I repeat? Okay, I'll just show with an example or something. So for example, if you have n equal to 3, then the number of ways to tile what you can do. So like one thing is you can take all the tiles you can take are red. I mean, it can be this type of thing. So now this has 2 choices for red and green. This has 2 choices, this has 2 choices. So you get 2 cube equal to 8. And then also you can do is, this is 2 and 1. So this is of course blue, and this has 2 choices. Or you can do it ulta. This is 2, so this is sort of 10. Oh, sorry, 12 addition.
Are tilings upon reflection considered distinct?
Sorry?
Are tilings upon reflections considered
Yes,
distinct?
they are distinct, they are distinct. I mean, you are looking from here always. This is the start. So, and you have to prove that Tn divides T of 2n plus 1. So, does everyone get the problem? These are the tiles you are available. Guys, speak up. Yes or no?
Yes.
Nice. So like whenever you have any ideas, you can just speak up. Also, if you think I'm going too fast or I'm going too slow, any which way, just tell me.
I made a basic recursion for 1 by n.
Okay, okay.
So if we start off with the number of ways to make a 1 by n, that's t of n.
Yes.
So t of n, the last or even first block, if let's say blue is 2 blocks, red is 1 block, and green is also. So the
This.
last block can be either red or green.
Okay, so you are considering that this is one by one tile, first case.
Right. So this t of n would be firstly equal to 2 times t of n minus 1, because
Yes.
arrange the rest of the n minus 1 in t of n minus 1 ways, and the first one in 2 ways with either a red or green dot.
Yes. Right.
And now when we have 2 as in the blue block, it's just t of n minus 2.
Right. Right.
So this gives us a general recursion. T of n is equal to 2tn minus 1 plus tan minus 2.
Yes. Correct. So I mean, you can try to solve this. You will get something, but like I think it would be quite. This of course will provide you the solution because it's a general formula. But if you get something irrational sort of, which to the power will then make it square, it would be hard. It would be hard to prove divisibility, right? So like try to think of like of course you have to do recursion, that's true. So you can try to think of recursion in terms of Tn and T2n plus 1. Like how would you try to relate T2n plus 1 with T2 Tn? Try to
Right.
relate these two. Yeah.
So the recursion for t of 2n plus 1 would use t of 2n and 2n minus 1. We can break those up further and see if at the end we get something divisible.
Okay. I mean, fine. But that would just, increase, like you will have to do a lot of work. Like let's say T of 2n plus 1 equal to 2 T2n plus T2n minus 1. So again, you break this into what? T2n minus 1 plus T2n minus 2 plus this, you get 2 minus 2. So this is 3 plus T2n minus 3 sort of it. If I didn't make any mistake. So like you see, there are a lot of branches. So you'll have to do a lot of computations. Try to think of a like just how you related Tn with Tn minus 1 and Tn minus 2. Can you relate T2n plus 1 with Tn? Can you relate these two in some sort?
Okay, I'll try that.
Yeah.
I tried that for
Yeah.
the 1 by n block. So for the 1/2 n plus 1 strip, we can divide it into T of n for the first n blocks, the second n blocks, and the last block.
Okay, but are you sure that would work? Are you sure allowed to do that? Because, okay, are these odd? These are not odd. So if you, let's say, what is this? 11, so like it's 5 and 5. So how do you know that there is not some block like this? You would be missing out on cases like this.
Right, so we can account for those cases also
Okay, okay.
to see if they're in terms of T of n.
Okay, yes, I get what you're saying. So just a thought that you want to show that Tn divides to T2n plus 1, right? So why if you get one Tn even that is fine. Why do you need to do this and again this separately? You can just take all of this as Tn plus 1 because we get one Tn and that's what all we care about. Does that
I
make
see.
sense?
Okay, so you're saying you split it up into Tn and Tn plus 1,
Yeah,
and
this
then
is it.
also account for the case where there is a blue block in between both of them.
Yes, yes, yes. So this is sort of case 1, uh, and case 2 would be. Wait, where is your answer? Gosh, I can't use this. So case 2 would be something like. Isn't there some select option? I can copy paste this. Okay, leave it. I'll just draw here. So in case 2 would be there is a block like here, or yes. This is case 1 and this is case 2. Okay, so like what would this give you? This would give you number of ways to type this is Tn plus 1. This is what.
So it divides by Tn, the
Yes,
sum of.
true. Right. Did everyone get this? What we do? Yes, yes, yes. Don't need that is correct. What?
It should be
I think
times T of n times T of n minus 1 because there's one thing where it's in the center and the right half and center and the left half. And that gives two distinct possibilities.
wait,
Because like
What?
Because like the thing with the domino can cover the center and the square in the right half, or the center and the square in the left half. And I will
No, but if it covers center and the square in left half, it is already covered here, right? Or am I wrong? Like just if it is something like this, then isn't it already covered here? Because 1, 2, 3, 4,
no, because Tn times T of n minus 1 is counted, has to be counted twice, right? Like,
Right.
That's
So
just
there is
correct.
two
Like
cases.
because
what's that?
if it's over here, then we get Tn minus 1 from here and T of n from here. And if
yes.
But that
and if
counting is covered in the previous case. Like the entire thing, like it's just like you're starting Tn
Yeah,
plus
that
with a
that red thing is already covered, right?
uh,
Or red thing is covered in the first case.
yeah,
This is correct, right?
Yeah, because the domino already comes in Tn plus 1.
yeah,
Yes. Yes.
my bad. But wait, there's another way you could do it also. If they in the center there is 1, or if in the center there is 2. That would the first one will give 2 times T of n whole squared, and the second I think
Yeah, I mean like it's
yeah,
just similar case, right? Like it's you will get what 2 tn square plus
2.
if you go there 2 tn minus 1 or something like that.
Yeah. But wait,
No,
then
or
with this recurrence and that recurrence combined, I think you can get some.
no, this will be 2 tn square, I think. Like middle square can be red or green.
Yeah.
Yeah, I mean something like that should work. Yeah. Okay, so
But
like these were the
that can actually give us a neat formula that will help us calculate the explicit value for
if you want a recursion, then like this formula is good enough. Oh wait, not this.
yeah that will
This formula.
that with the
Yeah.
function.
That will thing will give you something. I mean, true. Okay, so like we will move on to next set of problems. Like these are sort of problems where points or things are colored and you have to show some existence of triangles, squares, something like that. Okay, oh by the way, this what we did above was a sum in more question. 2018 or something. Okay, so now so the next question is um the, there is a 5 by 5 cross 5 grid of points. Are these 5? 1, 2, 3. Okay, yes. And each of these points are colored using either red or blue. You have to show that there exists a square with sides parallel to the coordinate sides. I mean, sides are either vertical or horizontal, such that all the three like wait, at least 3 of the vertices have same color. Did everyone understand the question? Did everyone get the question?
So in the square which we have, suppose
Yeah.
I have, if the answer is a 3 by 3 square, so at least
Wait.
3 of the vertices, do you mean vertices of the square, or they could be also
Yeah. They mean vertices of the square.
So if any 3 of them are red in the vertices of of the grid, then that's not with the condition.
I mean that's what you have to prove that. So this is to prove. So like each of these points are colored either red or blue.
Does it have to
And
be a unit square?
sorry,
Does it have to be a unit square, or can it be an arbitrary square?
it can be arbitrary square.
Okay.
I mean, it of course is not unit. You can just color this chessboard fashion.
Oh yeah, makes sense.
So like, so now then you have to show that there exists some square. Like for example, this is a square, such that at least three of these vertices share the same color. Or even all four can be the same color, but at least three of them. Is the problem clear? Okay, so like just a general strategy for proving such problems is you assume for the sake of contradiction that this does not happen, and you have a coloring such that this is not true, and then you use some PHP sort of arguments or something like that to show that this cannot happen. Okay, wait, my bad, sorry. These sides may not be vertical or horizontal, I think. Very sorry, my bad. Let me just check. I forgot. It is mostly not true. Yeah, they need not be of the same. They need not be parallel. I mean, just to clarify, you can have a square like this or something. There is the plan. So you can have a square of something like this also. What is like this is a valid square. Okay, so like I just start the argument and you can finish. So like for the sake of contradiction, assume that this is not true and you can have a coloring such that any square you find, you have exactly two vertices of each color. So the advantage of this is that if you find some square whose two vertices you know are to be red, then you can clearly say that the other two vertices are blue, right? Or vice versa. Let's just start with, let's say the corner squares we can start with. So we can have two configurations possible, right? This can be the blue, blue and red, red, or it can be blue, blue and red, red. Try to deal with these separately. Okay, also like general statement. If you have solved the what? Okay, nothing. Sorry, continue. Okay, sorry, I remembered. So if you have solved the RMO last year ka RMO ka sixth question, that was the 4 by 4 4 cross 4 grid with 7 points colored blue. This is actually a much weaker statement than that. I mean, you will immediately realize why, but like it is a very much weaker statement, but it also has a simpler solution. So as an exercise, you can try that at home if you haven't already solved. Okay, any ideas, anyone? This is a pretty straightforward question, so like you can get it. So like let's say we are dealing with the first case. This is blue, this is blue, this is red, this is red. Now, I mean, you want to move symmetrically because that would make life easy. So this point can be either blue or red, that doesn't matter. So we can assume it is red. So now what do you get? You get this, since this is a square, these points must be blue because you have assumed it's not true. Similarly, these points must be also blue. Oh, okay, sorry. Turns out that statement was correct. It has to be vertical and horizontal. So like you get that so from this square and from this square, you get that these are blue, these four vertices are blue, but like then you get this square where three of these are blue and one is red. So that's a contradiction. So this is how you do the first case. Anyone wants to volunteer for second case? Like it's pretty much same thing. This is the second case, by the way.
Yeah, I can try.
Yes, go on.
So we can again assume that the middle point is either red or blue, supposedly red again.
Yes,
So now the top, the if I say the top right square and the bottom right square,
yes, these
we
squares.
break it up into quadrants. Then each of the other ones must be blue.
True.
So now we need to fill that one red, the other one, just in order to keep that. But then we would get a blue square. So
But sorry, could you repeat the last part?
but then it seems that we need to use the vertical and horizontal thing, vertical and horizontal case, because this shows every one is correct.
No, no, like you also have these points, right? You have to also color these.
You can take the middle of each of these squares again.
Yes, true. So if you observe this square, like just take the 3 by 3 square. Now this has the configuration of the first case, right?
Right. So we
In
need
the
to
corners, yes.
case we need to prove that there's always a case where there is the opposite corners are the same.
You just did that, right? You did the same thing. Like these were forced.
Right. So in other
So
words,
you consider this square now. So this square without loss of generality is red. And so these must be blue. And so you get a square, right?
right.
Yes. Did that make sense?
Yeah.
Nice. Okay, so like as an exercise, you can try this at home, RMO 23P6. RMO, I mean normal RMO, not the other RMO.
Also, Arnav, like RMO 2020 P3, like P6 is actually the same as this problem. Like both are equivalent.
Are is same as?
Yeah, like this problem actually proves the 2020 speech. P6.
Actually no, like that thing had something else. That thing has had 4 by 4 cross 4 thing.
Yeah, like that's the only difference. Otherwise,
No,
the
no,
problem.
and seven, exactly 7 points were color. So like if you get a square with 3 non-colored points, that's not the same thing.
No, it asked you for no, like yeah, but with 7 points you can actually like that is just PHP argument. By PHP argument you can
Yes,
prove
yes,
that a
but
square.
that's a different argument.
Okay.
I mean,
And
this is not the same problem, right?
that one, the triangles are allowed. Like, that messes.
What? Sorry?
In the RMO one, tilted triangles are allowed.
Yes, yes,
That's
right. Tilted triangles are allowed there. That's why, like, if you allow here vertical and horizontal, you just cancel, then you can just see that it is the same thing. It is the RMO.
the source of this problem.
Oh, this is some INMO or RMO. I don't remember. I don't recall actually. I might have to check. Okay, so like let's go to the next question. So this is a very interesting question. Like the structure is quite interesting. So we consider, where is the magnetic field? So we consider in consider the Cartesian plane and the lattice grid. Like I hope everyone knows lattice grid. It is just a set of integer coordinates. This continues, this continues. Again, you have same thing. I'll just draw some for the sake of completeness or something. Okay, so now you are given that these are colored using three or that this is the lattice grid, like it extends indefinitely on all the sides. You are given that each point is colored using either red, blue, or green, and each of them is used at least once. What is this? Okay. Each of them is used at least once, you know that. And then so also you are given that 0, 0 is blue. Wait, that blue did not get select. Yeah. You are given this point is blue and this point is red. Show that there exists a right angled triangle with vertices of different color. And like they here, I'm sure they need not be parallel to the side, so you can have a tilted triangle. So you can have something, a tilted triangle. Okay, this is the y-axis. This is the x-axis. Did everyone understand the problem? Nice. Okay, so now clearly like this chart is the same thing. You assume with FTSOC, this does not happen. And try to figure out where the green point can lie, where the green point can't lie. Okay, so like any ideas on where the green point can lie, it cannot lie.
The green point cannot lie uh, on the x-axis and on y is equal to 1. Those two lines.
Yes, correct. So like any green point cannot lie here, green point cannot lie here. What about some point like this? Can the green point lie here? Like let's just assume it can. What can you say about the color of?
Because then the foot of its altitude I must think will be blue or green.
Yes, yes, true. So this this what you call this point you can see that this point cannot be blue because otherwise you get this triangle. It cannot be red because otherwise you get this triangle. So it has to be green, right?
Right.
So in any case, you get a green point on the y-axis. Like if there is no other point, it has to be on y-axis. Because green is used at least once, we know that. So if green is used anywhere outside the y-axis, you can drop a perpendicular and that has to be green. If it is not used anywhere outside, it has to be used on y-axis. So you get so like we can just erase this point because we don't need it anymore. So now what can you say about this line? Like what can you say about points on x-axis? We know that there cannot be green points on x-axis. Can there
Right.
be?
Can't be any red points.
They must all be blue.
Yes, because there cannot be any red points, otherwise we get this triangle. So you get that this whole line is blue. Similarly, upper ka line is whole red. Now can you spot a right angle triangle with vertices of different color? Or note that they need not be parallel to axis, so you
Wait,
can have something
you,
like
I
this.
think you can take a green point, a red point, and a blue point on the tree. Because like
So,
you have a line parallel to the x-axis, which is all red. I think you can take a point there and a point on the
yes.
okay.
So we can just construct things like, I mean, anything literally works, but just take 45-degree lines. So they pass to integer points. So you get a blue point here. What is happening?
Are we dealing with lattice points or all points in the plane?
What? No,
Are
we
we
only have lattice points.
okay?
So you take these 45-degree lines. So because they will pass through lattice points, so this point is red and some skill issue my laptop has. We can't work 1 minute. Wait, I'll just change color. And this point has to be blue. So you get blue, green, red. That's it.
Another construction could be like it goes one to the right and however much down so it reaches the red, and then when rotating about 90 degrees, the new thing will have like a downwards and -1 and right of an integer with the slopes of multiple.
Yeah, yes. Like I mean, you are just rotating this, right?
Yeah. No,
Yes.
you
No.
go like can I draw on the screen?
Oh, yeah, sure. Okay.
You go like this and then you rotate about 90 degrees to get this, and we can easily check that this is a lattice point because slopes multiply
Okay.
1.
Okay. Yes. True.
So that's for the general case.
Yeah, I mean, you need only one triangle. You can construct it anyhow
Wait,
you
what
want.
if all points on the y-axis are like
All points on y-axis are.
of the same color? Oh, but then we can choose a y-axis so that there are two of different colors.
There cannot be, right? At least each color is used at least once. And you
Yeah.
showed that if there is a green point outside, the perpendicular must be
Yeah,
green.
no. What I was saying is in the beginning we took a blue and red on the y-axis, right? So I was asking what if it doesn't exist?
No, it was given. It is
That's
given
like
data.
no, because I was thinking, what if we choose a y-axis so that
Okay,
blue
okay,
is, then I was like we change our choice.
okay, then something will happen.
And if we keep the blue and the red, if suppose the blue stays at the origin, where else can we move the red point such that this holds?
Interesting. So,
It doesn't
okay,
matter
so
if the red point is
yeah.
a blue point or below.
So if you get any two adjacent blue or red points, you are done, right? Because this is just the same case everywhere.
Right,
Or like even if you get any two adjacent not discolored points, you are done. Like, but is you will have that, isn't it obvious?
right. Yeah.
Yeah. So like just given this data is enough. You actually don't need that. These are like this. Did everyone get the proof? If there is any doubts, just speak up. Wait, what happened? Thanks.
Got it.
Thanks. Okay, so let's move to next question. So we will move to game type questions. You had a class on combinatorial games, I understand. So we'll use A and B. Like we can use Bernardo because I liked it, but it's very long. So let's just use A, B.
Use Calvin and
So what?
Calvin and Hobbes.
No. It's either Bernardo or it's AB. Or maybe Alice and Bob sometimes.
Akbar and Bilber.
No, never. Okay, so like, okay, this is one good question. Point is, I don't know the source. So you have a 2n plus 1 cross 2n plus 1 grid. And is this 2n plus 1? No, it is not. No, it is. No, it should not. Is it now?
Yes.
Nice. Okay, so and there is a, okay, I'll just not say checker, I'll say a piece. So there is a piece at the center square initially. Alice and Bob take turns moving this piece. So Alice plays first turn, Bob plays second turn, Alice third, and so on. At the ith turn, the player can move the piece. I places to left, right, top, or bottom such that it remains on board. Ith turn ko player will move piece I places to one of the four directions, and like it should not go out of the board. And the player who can't make a move loses.
Wait, is it moved I steps to the right?
What?
Is it moved like one step or I steps?
At ith turn, it will move I steps. I mean, first Alice will move one step, then Bob will move two steps, Alice three, Bob four, so on.
Well,
Did you get it?
actually in the result, Probably was an evil magician and a wizard.
What? What?
If I remember correctly, in the original problem, I think it was an evil magician and a wizard.
Is it? I don't remember.
At least when I first saw it.
What's the source?
I think it was in the Sophie mock, Armo one.
Ah, quite possible. Like one of my friends was solving and he asked me this problem later, so it's quite possible it is from them.
And I think it was in something like a lava mode, and then it fall into the lava if they can't play a turn. So that was something like that.
Oh, nice. Okay, like let's just experiment with small cases. Let's say n is equal to 1. This is the 3 by 3 grid, that means. So let's say Alice goes here. Bob will have to go here. Alice can't do anything, so Bob wins. If n is equal to 2, 5 occurs. Okay, so let's say Alice goes here. Where do you want Bob to go?
Wait, so Alice and Bob, just to clarify, they both are not on the same, or are they both on the same square?
What do you mean same square? Like Alice moves the piece here, then Bob will see that the piece is here and he will move, let's say, here. Then Alice sees that the piece is here, so she will move the piece, say, here because 3 squares.
Oh,
Then,
right. Okay, so Bob moves where Alice stops, and Alice moves.
yes, yes,
Okay.
yes. Okay, so like, of course, if Bob plays this, then Alice plays this, and Bob loses, so Bob won't play that. So if Bob plays here, Alice plays here, and Bob plays here, so Bob wins again. Okay, so like, what can you tell me an upper bound on how many maximum number of moves can be played?
2n plus 1.
Are you sure? Like let's see here. How much many moves we played? 1, 2, 3, 4.
Right, the last move is not counted.
It's 2n. So and like the proof is pretty obvious because at the 2n plus 1th move, Alice will have to move 2n plus 1, but like there are no squares with distance 2n plus 1. Because from here to here it's just 2n. So like can you show some strategy that and also like from the initial experimentation it looks like Bob is winning, might be true, might not be true. So like can you show some strategy for either Alice or Bob?
Well, Alice's first move doesn't matter because wherever he goes, it's the symmetrical.
Yes, yes, true. Also wherever she goes.
Right? So if Alice moves one step, then Bob has to start from there.
Yes.
So if Bob starts from there, then to maximize his number, he should always go to the side which has the most number of squares.
Yes. True.
So this should follow for every person. So it should always go kind of, if it's limited, it's
Like,
obviously
Greedy
it would,
algorithm may not necessarily work. Like short-term gains may not help in the long term.
Oh, but like we want to show strategy. So like if you get some local idea, you can then generalize it.
right. So like for cases, for if you start thinking of the best possible case from every move, it would- it would, according to me, if I checked some cases, it would may look like a spiral. So,
Like not exactly a spiral, I think. I mean, that would depend on where Alice moves, right?
but it's symmetric, right? You're talking about the first move.
No, no, no. Like, so Alice moves first move here, let's say.
OMC, combinated stuff.
Oh, so he retraces back. She retraces
Yes.
back steps. Oh,
No,
yeah,
no. Bob is he.
Sounds softer in this keyboard.
So
yeah.
Bob goes here.
Sounds softer actually.
Athar, like, are you speaking to us or
Oh no, sorry.
no problem, no problem. So like, Bob goes here, right? Now Alice can go anywhere. I mean, okay, here I think she has only one choice, but anytime. Like maybe she could have gone up or something. But like then by this argument, Bob should come back, right?
Right.
Can you show that this strategy always works? This is the correct strategy. This is the right
You
one.
repeat the strategy.
So now from experimentation, we got the idea that people who are, I mean, not people, when Bob should, you know, go anti parallel to what Alice did, if that makes sense.
They should stay on one line, kind of one row.
Yeah, Bob should just retrace Alice's step and go one move to the left, one move ahead.
But like, what if Alice is already on the bottom row? Then that would.
Yes.
But wait,
That's the only issue.
but wait, that,
So
I don't think Alice will ever be on the bottom row because
I mean, yes, that's true. Like she can be, but that's then you can just say by this argument that it's the last move.
what I was thinking is like the only way Alice is on the bottom row if it's like Bob and moves into the bottom. Oh yeah, that's the same thing because then it would have taken and moves and then
Yes,
yeah.
yes. So the thing is that if you just follow this strategy, you will observe that every time, like Alice will require at least uh 2n steps or 2n minus 1 something. What?
Right. So because there's always an even number of turns.
Yes. So after 2n steps, Alice will have move at Alice will be at move after 2n steps when the piece is at the one of the rows. Till then, Bob can follow this argument, but then after that, after the 2n plus 1th move, Alice cannot move anywhere because the board is limited. So and Bob can ensure every move until there are 2n steps, and we know that 2n plus 1th move cannot occur, and hence Bob has a winning strategy. Does that make sense?
Yeah.
Right. Okay, so let's move ahead. Okay, wait, let me check how if I have any game. Or like, okay, we are short on time. Let's just do a quick game. Okay, let's do this. So what we have is you have a board. Like let's say this is an M cross N board. There is a rook placed at the corner square, and at every turn, Alice and Bob take turn moving the rook. Alice and Bob, and like everyone knows how rook moves, right? So Alice and Bob take turns moving the rook. And the rook cannot visit places he has already visited, like cannot repeat squares. And the player who cannot make a move will lose. Wait, what's happening? Player who can't make move loses. So determine who has a winning strategy.
Places that are visited, does that mean like if suppose the rook moved 4 steps front, are all of those 4 steps
No,
and
no,
the
no. Only this one gets counted.
Could you
only
repeat
when
the
it's
problem?
10?
Yes. What? Sorry, Athar.
Could you repeat the problem?
Yes, so like it's similar to what I gave as the buffer problem, but it's a bit different. So this is M cross N grid. Uh, Alice, this is a rook at a corner square placed initially. Alice and Bob take turns moving the rook. Same square, like square cannot be repeated. Player who can't make move loses. Yeah.
Wait, this was in Agamjeet's Vyas pasta.
Yes, true.
Yeah,
Yeah,
I solved it today morning only during the mock.
bro, that's cool. I mean, I solved that last week, so I was like, okay,
Could
this
you
is
send
nice
another
problem.
buffer problem?
You solved the previous one for
Yeah.
that case also.
Oh no, not yet. I'll do that.
Okay. Yeah. Okay, wait. Jaditya has some. Yes, yes, that was the argument essentially. True. Thanks.
If every move they move 1 step to maximize
Yeah.
the number of squares, then it will just be alternating A B A B A B A B. So
Okay.
A will have the majority. So in the end, it would be B if that's the case, because they would think of moving 1 step to maximize the number of squares.
Like what do you mean maximize? Because at every step only one square gets covered, right? Like even if you move the rook here or you move the rook here, like either here this square gets cancelled, here this square gets cancelled. Every time it's the same, only one square gets cancelled.
Right, right. Right.
Wait, does the first guy win when n is even?
I think so. No, no, no. Oh, yes, yes, yes. True. Was guys.
Hmm. What?
Yes, yes, that's true.
And the second one wins on its own.
Yeah.
So every time, either way, if suppose A lands at a particular square, we label that square A.
Okay, okay.
Or suppose A is red and B is blue.
Hmm.
So we color the square where A landed as red and we color the square where B landed as blue.
Okay.
So every square at the end will either be red or blue.
Not necessarily. Like they can just end before every square is covered. Like for example, let's say Alice moves here, Bob moves here, Alice moves here, Bob moves here, and now Alice will move here, and then Bob will lose without covering the whole board. Okay, no, he does not lose actually. He can move here, but like something like that. You get the argument. Like for example, all these squares are covered, these squares are covered, all these squares are covered, and then you land here. Now you can't move anywhere
Yeah.
without covering the whole board.
So
Okay.
if all
Hmm.
of them are in one case, if all of them are either red or blue, then it's clear that Bob can't move. If the case is that every square is filled.
Are you considering case Mn is even or Mn is odd? Mn is even, I think, right? Or no? Okay, Mn is because that would depend on parity of Mn.
Oh, so it's not a square. Oh, right. It's not a square. Yeah.
Okay, so like I think we have some short on time, so I'll just give you the idea. Wait, what is happening? Why can't I scroll? Yes, okay. So one thing is, so you get that you have to make cases. Mn is odd, Mn is even because this is what I call the parity sort of thing because Alice Bob are two players. So let's say Mn is even. So what you can do is you tile the board using dominoes. Like I hope you remember what dominoes are. So something like this. And he starts here. So now Alice will move the rook here.
Another solution I got during the mock I gave, you could do something like copying, but instead of in dominoes, you do it across the x-axis reflection. That's only
Oh,
works.
okay. I actually thought of that, but I was not very sure because I mean it works here. It works when Mn is even, but it
That
does
only
not
works
work when
when
Mn is odd.
yeah. I spent quite some time in the contest trying to generalize it to an odd until I got the domino there.
Yeah. So like what you can do here is so Alice moves here, and now wherever Bob moves, Alice will just move to the corresponding square on the domino. Like if Alice moves here, I mean sorry, Bob moves here, then Alice will move here. If Bob moves here, Alice will move here. So every time Bob plays something, Alice will move to the corresponding domino square, which is always vacant. And so when Mn is even, you get that Alice wins. Is this clear?
Yes.
So, and other case when Mn is odd, so what you can do is now leave this square and tile remaining things using dominoes. So now Bob will repeat the same argument. Wait, what is this? Yeah. So now Bob will repeat the same argument which we did here, just that now, so wherever Alice moves, let's say Alice moves here, then Bob will move here. Alice moves here, Bob will move here, Alice moves here, Bob will move here. So now Bob has the same argument, so Bob will win this time. Does that make sense?
Yeah.
Okay, nice. So like I think we're already over time. I'll just give what you can try at home. Like maybe if you haven't solved, try in Mo last year ka 2024 or 3. Yeah,
4 P.
4. Yeah, P2. So you can try this. Also, like I told about RMO 2023 P6. And wait, let me check. There was like the buffer problem I gave.
I
I
am
had some shorts.
2023 C6 is good.
Yeah,
What?
and if you people have time, 2009 C6 as well. Do that.
Oh, okay. Okay. For sake of Mandar, I will just write it.
And 2023 C6.
Okay. Do this. I mean, okay, you can try this, no problem. Also, like one another good problem, like the buffer problem I gave above, is something like
2021
Soviet Union
2021 C6 is also.
meetings. What is 21 C6? I don't remember. Okay, Atharva says it's good, so let's just write. So like this is actually good problem. Like it's very much similar to this, but it's a bit different. So you can try this for sure. Try this, try this, try this, try this.
What is the
Okay.
last one? SC 2000.
Shortlist 2021 C6. I mean, okay, try these only if you are very much confident about these.
2021 and 2023.
I just wrote this to please Mandar and Atharv. So like first like just focus on these first. And if you are very much confident and very much enthusiastic, you can try these. Okay, I'll stop share. Yeah, there is something in chat. What is that in chat? Okay, no one's here. No problem. Okay, so I hope you enjoyed class.
Yes.
If there are any doubts or something, I'll here for some time if you want to ask.
Class was good.
Yeah, thanks. I mean, only class was good, not handwriting. That's fine.
We didn't talk about handwriting.
Sorry?
So you took inspiration from Malay. Class was good.
No, Malay writes way better than this. I mean, what was that?
Malay on a bad day, his handwriting is bad.
Bro, like I can't write. I mean, this is my handwriting even on paper, you know. You
Wait,
saw
should we
that
not
yesterday.
stop recording now?
Okay, yeah, that's the good point. Wait, when I stop recording, will this be uploaded to my cloud?
What?
Will this
No,
be
it
uploaded
will be uploaded to the Sophie Cloud, assuming you did it from Sophie.
OMC cloud?
That.
Okay, I'll just stop then.